Hola, sí? Hola, buen día. Good morning. So today it's our now I don't feel the words. Okay. How is it called? The official name of this talk? Periodical lectures. So today, as a periodical lecture, we have Ignasi Ribas that will show us a field that we are not very used to that, which is, I think it's nice, but maybe we can find some
Who knows?
some common interest. Okay. And Ignasi Ribas, we know each other for many years. We did our degree together. Okay, so I was just copying his writings. Okay, and he's now the director of the Instituto d'Estudis Espacials de Catalunya, and he's also a research professor here at the Space Institute of Space Science, or Institut de Ciències de l'Espai here nearby, which is a CSIC institute. And he did the PhD also at the University of Barcelona and then a postdoc in the United States. And he's an expert on research about exoplanet, I don't know, analysis or how you call it. Yeah. Okay. So please, Ignasi, go ahead.
Okay.
And thank you for coming.
Okay, so thanks for the introduction, Albert. Yeah, indeed, we go back a long time, actually. So we know each other. And I have some connections here with ICMAB as well. Some people I collaborate with. Also the son of Teresa Puig works in my group, actually, now as an intern. And also with Lourdes Fábrega. And I have some neighbors here from my neighborhood. So it's really nice to be here and to give this talk. And as Albert said, I will be talking about exoplanets. Don't worry, it's not going to be a technical talk. I know that you guys are not experts on this. I try to put also a bit of edge in instrumentation so that you know what's going on and maybe find potential interest that may be here in common. So this is going to be a lot of introduction, let's say, and a lot of background. So let me start with how we do it to detect exoplanets, detection techniques, which is one of the main things here. And the thing is that there's no, if exoplanet detection was easy, it would have been done for a long time. Let's say this, hunting for planets is something that humanity would be doing like for centuries probably. And so the naive idea of going to a star, pointing a telescope and taking a picture is just not possible in general. And it's not because of the contrast, right? So the glare of the star is way much higher than the emission from the planet. Actually, the Earth versus the sun, the brightness of the Earth is about 1 billion times less than that of the sun. So if we were to take a picture, this would mean removing 10 to the 9 photons and then remaining 1 photon that will be coming from the Earth. Therefore, this is still impossible. So what we do in general to detect exoplanets is to resort to a different technique, which are the so-called, the so-called indirect techniques, meaning that we don't take pictures of planets generally, but we take measurements of stars and see how stars vary, and that variation can be attributed to the presence of an orbiting planet. And that variation can be velocity, can be brightness, can be position, and other things as well. So this gives rise to a number of so-called indirect methods. I'm going to be discussing some of these. See if I can find the pointer here. Yes. The radial velocities, Doppler effect, transits, brightness changes, astrometry, position changes, and then some other more exotic ones, timing, which I'm not going to be discussing, or something called gravitational microlensing, which uses Einstein general theory of general relativity. And there are some exceptions where we can take pictures of planets. In some cases, when the planets are very young, very bright, very big, we are able to remove the light of the star. In that case, the contrast is about 1 in 10,000, 1 in 10 to the 4, sometimes 10 to the 5. And there's enough photons then from the planet to actually get actual pictures. So, but for the most part, most of the discoveries that we have until now, which I'm going to say the number already, that's 5,800 exoplanets known as of today, have been discovered using these techniques. It's a lot more complex, and this is a sort of a famous diagram. This is it was devised by Michael Perryman here. And all these branches down, this is like a sort of an octopus kind of shape. And you see different methods, dynamical, microlensing, photometry, and all these branches go as far down as they can go in terms of planet masses, let's say 10 Jupiters, 1 Jupiter, 10 Earth masses, 1 Earth mass. And so then some techniques that get to the Earth mass domain, some others stop at the Jupiter masses and so on. But this illustrates that the number of indirect techniques is huge. It's only about measuring changes on something, on some variable that can be attributed to the presence of a planet around in a system. So in terms of radial velocities, and I'm sure I have to give very little background here, we're talking about Doppler effect. So we have a star with an orbiting planet, an invisible orbiting planet. So they both orbit around the common barycenter. And if we have a telescope pointing at this system, again, we don't see the planet, but we do see the star. Sometimes the star is receding from us, approaching towards us, receding, approaching, coming and going. And this wobble motion is what gives away that the star is orbited by a planet. So if we see a star that's wobbling, let's say back and forth, that may be because it has a companion. And if that companion is small enough, then the wobble will be small. And one can measure actually the minimum mass of the planet, right? So this is the minimum mass of the planet. This is the so-called radial velocity curve, which has an amplitude. And then from the amplitude of this radial velocity curve, knowing the period and knowing the stellar mass, one can obtain the minimum mass of this planet. And I say minimum because there's a degeneracy with the inclination. So the radial velocity component of, let's say, an edge-on low-mass planet will be the same as the radial velocity component as an inclined, more massive planet, let's say. The component will be the same. So what we get is m planet times sine I, with I is the inclination. And it's 90 degrees, which is completely, when it's completely edge-on. And of course, the measurement principle, I'm going to explain a bit more detail. This is just the well-known Doppler effect. So we can measure velocity shifts by measuring wavelength shifts, one of those red-shifted and blue-shifted. So to put this into a bit more detail, this is the spectrum of the sun. So these are a star from the red to the blue. And you see all these vertical dark regions. These are spectral features. These are lines associated to some chemical constituents, typically atoms. And whenever there's a line, there's a transition from one of these atoms, and then there's a obscuration, and these are these spectral lines. So we do a horizontal cut of one section here. What we have is a relative flux as a function of wavelength, and all the little dips here are lines associated to some chemical, so typically atoms, right? So this is neutral iron, neutral helium, ionized titanium, magnesium, and so on and so forth. So each of these features correspond to an atom or a species, let's say, on the atmosphere of the sun. And you get this because it's a black body, but it has a temperature gradient. And therefore, there's some flux that comes at a position, some absorption, and then you get the spectrum. So let's now home in and try and see what's happening at the bottom of these lines. Remember that we have to determine the shifts of lines, right, to determine the radial velocity motion. So delta V over C is delta lambda over lambda, right? So let's see what it takes to find an exoplanet. And we're talking exoplanets, if you do the math from that calculation, that equation there, we're talking about meters per second. So determining meters per second motions from these spectral features. So let's try and see what this means actually on a measurement. So this is the bottom of one of these lines, right? So we have a few nodes, which is the location of the readout. This is normalized flux, and this is wavelength. You can see this is hundreds of an angstrom. And this is, let's say, steady state. I'm going to apply a shift of 3 meters per second, which is typically what it takes to find Jupiter-sized planet or some Neptune-sized planets. And that's it, right? This is 3 meters per second. So you can see the little thing moving there. So this is what is a displacement of 3 meters per second at this scale. And it gets worse because the measurements are actually this, right? So each of these nodes corresponds to a pixel on the detector. Each pixel registers some counts, photons or electrons, and then this has some uncertainty, and therefore we have to determine these motions from these kinds of measurements, which it's impossible, right? Yeah, I thought you'd say that. Why is it possible that to get to these precisions, and much better actually, we get these days to precisions of order of 10 centimeters per second, so more than 10 times better than this. And the solution is on this previous plot here. It's here. It's not one line. It's thousands of lines. So all lines move at the same time. This is Keplerian motion, so it's a whole star that moves to some velocity. So we measure in one line, maybe we can determine the velocity to precision of 10 meters per second or so. But if we have 10,000 lines, then it gets 100 times better. because of this characteristic. So we can get to this meter per second precision by observing these motions on many, many lines at once. So that's what it takes to measure exoplanets. So how we do this, it's with spectrometers, right? So we have a telescope somewhere. There's some fibers on the focus of this telescope. These fibers carry light to this optical system. There's an shell grating that does the dispersion. Then there's another shell grating doing cross dispersion, some mirrors, and then we register the spectrum at high resolution, typically a resolution of about 100,000. So lambda over delta lambda, resolution limit 100,000. And then the real revolution here is that, well, any little motion or any little change on this spectra will cause shifts that are way larger than we're trying to measure. Shifts of order of tens or hundreds of meters per second at this scale. Means that we really have to be very careful at making the measurement. And the way that was found when the first planet was discovered was by shining some reference light through the same system. So in this case would be a thorium-argon lamp. And this thorium-argon lamp has some specific features. And then you get this is the spectrum. All this solid line is the star spectrum. And all these little dots are lines, thorium lines that allow us to, they don't move, let's say, they're super stable. And they allow us to get a wavelength solution that will be fixed. And that is the revolution that happened about 30 years ago that enabled the possibility of measuring velocities of stars at the level of meters per second. So what does it take to find exoplanets, as I said? So we're talking about, here's our solar system. This is the period of our planets in years, and this is the velocity semi-amplitude in meters per second. So Jupiter, 12.5 meters per second. Okay. Today, this is a piece of cake. Today, we do this routinely. Of course, orbital period, 11 years. So you have to wait for 11 years to close the whole cycle. Earth, it's not looking good now. 9 centimeters per second amplitude over a period of 1 year. 9 centimeters per second, we still cannot do. So we're still not able to find Earths, let's say. And if you go to even smaller planets, it gets really dramatic. So 8 millimeters per second velocity caused by Mars, for example, on the velocity of the sun. So this is way, way too low for detection, let's say. So the only planet that we can find, let's say today, would be Jupiter, actually, at an orbital period of 11 years or 12 years. And yet, already back in 1995, there was this discovery, the first exoplanet. I put first in quotes because there's some discussion. There were earlier detections of exoplanets as well. But this is a Nobel Prize paper, let's say, Jupiter Mass Companion to a Solar-type Star by Michel Mayor and Didier Queloz. And this is the discovery curve. So this wobbling motion, that's the radial velocity as a function of time, which gave away the fact that this star is orbited by a planet about half a Jupiter mass, about half our Jupiter, let's say. And they were taking measurements with precisions of order of 10, 15 meters per second, and see the amplitude here is about 60 meters per second. By the way, Didier Queloz will come to CCCB in May. So if you're interested in hearing from him about this Nobel Prize discovery and something else, I think it's 15th of May at CCCB. And Michel has also been here a few times. So I said before, Jupiter, 12.5 meters per second, you have to wait for 12 years. And these guys found a planet that has an amplitude of 60 meters per second. So it's way more than this. And I didn't say that, but the orbital period of that planet was 4.5 days. And that was a surprise, because this was a planet that should not exist. So what people thought in the 1990s was that all our planetary systems resemble our own. And our own planetary system has the sun, the rocky planets in the inner orbit, so Mercury, Venus, Earth, and Mars, and then the gaseous planets, the giant planets on way out on further out orbits, right? Like Jupiter and Saturn and so on. So they knew when they're trying to find these planets that they knew. The theory predicted that no planets would be found through this technique, unless they were working on this for like 25 years, collecting data. And sure enough, there was the detection of this planet that should not exist. The star was 51 Pegasi. The planet was named 51 Pegasi b. And this is Jupiter, like our own Jupiter, but really close to the star. And this is the prototype of a new kind of planet that's called hot Jupiters, let's say. And the period is 4.2 days. it's only at 500ths of an AU distance from the sun, from the star. So this is let's say 20 times closer to the star than our Earth is from the sun. And it has a mass of about, a minimum mass of about half a Jupiter mass. So this planet does not exist, this kind of planet does not exist in our solar system, and it was a new category of planets called Jupiters. So this is a story that shows that although theory was predicting that this planet should not exist, these guys went ahead and they looked and they found something that was supposed not to be there, but it was, right? And we now know that there's many, many more hot planets that we were actually expecting. I said that the main driver for this is machinery. And the main responsible for getting to this very high precision finding these planets is developing spectrometers, as I said. And I think it's to our audience like you guys, this is really interesting. I said that this 1 meter per second that we're trying to measure can be, let's say, perturbed by the environment, let's say by any change in the environment. So 1 meter per second means a delta lambda of 2 times 10 to the minus 5 angstroms. That's 15 nanometers on the detector. Remember that detector pixels are typically micrometers, and we're talking that this change is 15 nanometers. It's just 1,000th of a pixel that we're trying to get this position from. And it's actually about 30 silicon atoms. So we're trying to measure shifts in lines that are actually at the scale of the silicon lattice, actually, of our detector. And any environment change, 1 millikelvin or less than 1/100th of a millibar will produce this kind of effect. So what we do is that we enclose the optical system in an optical bench and a vacuum tank. We do vacuum there and we temperature control it to a level of about 1 millikelvin. That's the machinery that we're using these days to find exoplanets. Means that we have these super high precision instruments, these optical systems, enclosed and completely controlled environments. And then essentially we close them up and then we don't touch anything for like 2 decades. Because if we do, then it changes the coherence, let's say, of the time series. So that's what we're doing these days in terms of instruments. There's one instrument in which we have really worked a lot. This is so-called CARMENES. That's at Calar Alto in Almeria. And in this case, it's not one, but 2 vacuum tanks with a visible light instrument and an near-infrared light instrument covering these wavelengths, visible and infrared. And in our particular case, we're trying to find planets around very low mass stars. So planets are very cold, stars are very cool. And therefore, we're going into redder wavelengths to try and maximize the amount of photons that we collect from the star. So a cool star will emit more in the near-infrared than a hot star. And from this instrument, we have already found about 80 planets or so, and we keep going. So what is the whole current record holder, let's say? And one of the big discoveries was Proxima Centauri, which was discovered by Guillem Anglada-Escudé, and he's a member of my group here at ICE. Back in 2016, there was Proxima b, so the first planet around Proxima Centauri, with an amplitude of only 1.5 meters per second and a mass of 1.3 Earth masses. So it's actually an Earth twin of sorts. And even today, with an even more precise instrument, we have been able to go down to 35 centimeter per second detections, and a planet which has the mass 1/3 of the solar mass, which is about 3 times Mars, let's say. Sorry, the Earth mass. So this is the discovery curve from Guillem back in 2016, and this is today's measurements. So this is the same system, radial velocities as a function of time. This is with HARPS, this is with ESPRESSO, and this is the other planet, Proxima d. So this is the level, this is state of the art today, that we can get to planets that are about, let's say, masses below that of our own Earth, and amplitudes which are really, really low. And then you may say, well, but you just said that you cannot find Earths, right? Well, true, we cannot find Earths. We're finding planets that are similar to Earth, but around stars that are a lot less massive than our sun. So Proxima Centauri is about 1/8 of the mass of the sun, which means that it doesn't take as big planet to move it around, let's say, and to do the wobbling motion. So you have some enhanced detection possibilities. And also Proxima b and d are much closer to their star than the Earth from the sun, which means that then we can detect these kinds of planets. And we have these instruments, these spectrometers have become extremely popular. And we have this is a timeline of different kinds of these spectrometers. different names and so on. And there are many planned instruments to try and go and hunt for these exoplanets and get them and increase the numbers, let's say. The other technique, which is conceptually even easier, is the transit technique. And here we're talking about eclipses. So easy eclipses. Let's imagine that we have a star with an orbiting planet, and the orbit is exactly edge on compared to with respect to your line of sight. That means that at every orbit, there's going to be a point in time when the planet crosses the disk of the star from your viewpoint, and this happens here, right? So we have the planet crossing in front of the star, or here is a bigger one. When it crosses, when we plot the brightness of the star as a function of time, we have a dip, and then it goes back up, right? And this dip is called a transit or an eclipse. And this is another technique that is being used to find planets, and even better, to measure the sizes of planets, because the depth of this dip is proportional to the ratio of surfaces between star and planet. And therefore, the depth is our planet over our star squared, which means that if we have some indication of the radius of the star, we can measure the radius of the planet. So we can get a direct measure of that radius of the planet. And this is the first exoplanet with a transit, was discovered back in 1999 by David Charbonneau here. And this is the discovery light curve. So he was observing this star, HD 209458. And then at some point, there was a dip, which was about 1.5%. So the star became dimmer by about 1.5%, then back up, and then the star set, actually, because it was really close to the horizon. And this was the first exoplanet found to transit the star. And since then, we know about another 4,000 or so. And by David Charbonneau got the Kavli Prize this year, which is also a very handsome prize. It's $1 million. Actually better than a Nobel Prize, I have to say. But he was shared with another person. So anyway, in terms of transits, I said that we can measure the radius from a transit because it's the surface that matters here. And also we can measure masses from radial velocities from this Doppler effect. So in principle, for many of or a number of these planets, we can get masses and radii, which means that we can measure densities. And with densities, we can try to understand what planets are made of. And here you have planet radius versus planet mass, and all these little dots here are the known planets as of some years ago. You see here the stars are our own planets: Venus, Earth, Uranus, Neptune, Saturn, and Jupiter here. And you can see all these different lines are different chemical compositions. So this would be 100% iron planet, 100% rock planet, mixture, 100% water planet, this in blue, and one that would be planets that would be formed by made of gaseous planets, let's say. And you can see here is a trend already. So low mass planets tend to be rocky. There's some planets, intermediate planets, that can be either rocky or gaseous, and then very massive planets are always gaseous, right? So we can understand what planets are made of and try to compare these with the models that predict planet formation and try to guess what their history might be, right? So how we do to find exoplanets using transits? I mean, you have to imagine, you could go to a star, point a telescope, and then wait forever. Maybe there's a planet, but maybe that planet has an inclination that makes no transits. So you could be there waiting forever and no transits. So you have to go and look for stars that have edge-on, let's say, planetary systems. And of course, you cannot do that star by star. So you have to go and observe many stars at once, hundreds of thousands potentially, and therefore wait there and observe for weeks, months, years, and try and see to catch those transits. And we typically do that from space, right? Because from the ground, there's a night-day cycle. Imagine that you were trying to find Earth, and you're there waiting 364 days, and then when the time comes, then it's daylight for the transit, for example, from the ground. So that we go to space to avoid the day-night cycle, and also to allow us to point at a position in time and get very, very precise measurements. So the Pioneer mission was CO, which was working from 2006 to 2012. Then came Kepler, which was operational from 2009 to 2018. Then TESS, which is still operational. And then CHEOPS, which is also operational from ESA. So these are the missions that are now flying to try and collect measurements of brightness of stars and try to see all those little transits, which is actually a challenge because some of these are really, really shallow. The future we'll have another more powerful mission called PLATO. PLATO will fly, is an ESA mission that we are also working on. It will fly in at the end of 2026. And the idea is to collect a lot of measurements for stars that are very bright or bright-ish, let's say, over long periods to try and find true Earth analogues. So you want to find true Earth twins, so systems with a sun or sun-like star and an Earth. And that's really challenging. We have 0 for now. We have 0 Earth twins found for now. Maybe it's interesting to know that the depth of this little transit of one Earth in front of one sun-like star is about 80 parts per million. So one has to measure the precision, I mean, the flux of the star to a precision of a few tenths of parts per million to see these little dips, let's say. And this is what PLATO will do starting in 2027. So as I said, the idea, well, using transits and then getting also information on the stars themselves, it's way too busy here, but take into account that we're using photometry for transits, that this photometry will also serve us to determine radii, masses, and ages of the star, and then we will getting radial velocities from the ground, and this will produce planets with masses, radii, and ages of high precision. And this is really the goal here, that we can compare with models. PLATO should be able to find more than 4,000 exoplanets, and I said that today we have 5,800, so this is almost doubling the ones that we have so far, and about 100 of them with very high precision. So that's the goal for PLATO, which is now currently being built and will be launched at the end of next year, the year after that. So maybe for you to have a picture of where we are right now, this is, of course, a lot of the pictures that I show here, of course, made up, right? So we don't have any picture of a star, of a planet. But what we tell artists like Martin Barczyk here, can you draw what you think that the exoplanet collection might be? And this is his work of art. And this illustrates some ideas that there's lots of planets with lots of characteristics. And it's, let's say, what a surprising thing is that nature is able to manufacture planets in ways that we never expected, of all sizes, of all orbital properties, of all distances from their stars and so on. So it's surprising, actually. And the variety is surprising, and the fact that the solar system is not the norm is also kind of surprising. So these are the main things that we know so far, and just very synthetic messages. It seems that the number of planets in the galaxy is larger than the number of stars in the galaxy. So there's more than one planet per star, which is amazing, actually. So the fact that a star forms a planetary system around it is not really an exception, it's actually the norm. Right? In most cases, stars form planets. The most common planets, and this is not a surprise, are the small ones. So there's a lot less giant planets than there are small planets, let's say Earths, super Earths, and mini Neptunes. So they seem to be very abundant, let's say. Many stars have Earth-like planets, Earth-sized planets, let's say. I said this already, that planets are so abundant that even our nearest neighbor, Proxima Centauri, has a planet, Proxima b. And also we find that multiple systems are very common. So there's systems with more than one planet, like our own solar system. And this is especially so when we go to a low mass star. So small stars tend to have more planets than larger stars. And this is one of my favorite plots. This is the 5,800 exoplanets found so far, colored by the discovery method. You can see here transits, radial velocities, transit timing, and so on. Here is the planet mass or minimum mass in Jupiter masses, and here is the orbital period in days. So I plotted here also symbols of our pictures of our own planets in the solar system. So here's Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And you can see here something that should be very, very worrying, right? So I said, the solar system is not the norm, but seems to be exceptional here, right? How many little dots do we see around our own Earth, or around Mars, or on some other planets? We don't see any. The only dots that we see are here around Jupiter. So we do find Jupiter analogues out there, but we don't find Earth analogues, or Mercury analogues, or Mars analogues for that matter. And the explanation is that this is a very strong observational bias. As I said, our techniques are very efficient at finding very massive planets in close-in orbits because they're more likely to have a stronger effect. while we don't find, or we don't have techniques that work to find small planets in faraway orbits. So there's a strong gradient, let's say, in our detection efficiency along this axis here, which means that we don't see these planets yet, but we expect them to be there and to be there in very big numbers. So they will come eventually. And there's something else here. You can see clumps, right? So there's a clump of planets here, there's a clump of planets there, another clump here. There's, for example, if you take Jupiters, there's hot Jupiters here, and there's normal Jupiters there, but there's nothing in between, or very few in between. If you go to, in terms of the mass axis, we have Jupiters along this axis. We have massive, let's say, Neptunes and some Neptunes here, but there's very little in between. So that tells us a lot of things, how these planetary systems form, and these planets form and evolve. So the formation models want to explain these diagrams and why there's more planets here than here, why there's more here than there. And we have a very good understanding of how this works, let's say. How we form Jupiter-sized planets, how we form Neptune planets, Neptune mass planets, and why there are some gaps in this place. So maybe the main idea here for you to retain is that we didn't expect any of these, right? So I said we don't expect any Jupiters around close in, very close to the star, these hot Jupiters. And the reason is that they cannot form here. A star cannot form a Jupiter so close to it because there's not enough material for the Jupiter planet to grow, let's say. And the theory today explains it by saying, okay, all Jupiters form somewhere here, and some of them migrate. So they migrate inwards. So there's a migration, orbital migration, and those Jupiters that form there end up in these positions here. And that's fairly well understood, this theory of migration, which, by the way, our planets in the solar system did not migrate. Thankful for us, actually, right? Because we would not have Earth. Because if Jupiter came across, it would swipe everything in its trajectory. Sometimes people ask, well, 5,800 exoplanets, where do we find them? Well, in our galaxy, of course. This is our Milky Way. We don't find planets in other galaxies. This is a drawing of our galaxy with the nucleus, the bar, and the spiral arms. And we are here in some inter-arm region, in the outskirts of the Milky Way. And most of the planets that we found are in this little circle here, around 1,000 light years from us. And the distance from us to the center of the galaxy is about 20,000 light years. So the galaxy is way larger than the area that we've been looking for planets. And the 5,800 that we have are like in this circle. But interestingly, we have found already our nearest neighbors, right? So our next door neighbor is Proxima Centauri b at 4.2 light years. So this is the closest star right now to our solar system, and it already has a planet. Can you imagine how long? I mean, you can now think, okay, this summer on my vacation time, I may be thinking about going to Proxima b, right? For like, I don't know, for a sun, for a little trip. And if we take the fastest spacecraft that humans have ever built, and which is now Voyager 2, going to the stars, actually outside of the solar system already, and points Voyager 2 to Proxima Centauri b, this trip as of today would take 75,000 years. So the trip with current technology to the nearest star, so there's a lot more, it's about 75,000 years. So if when you watch movies like Star Trek or Star Wars or something, think about all these distances that are jumping around. And what it really takes for now, so who knows what humanity will be able to do for now to travel to our nearest neighbor. I said that we have lots of things that we know, and we also have a number of mysteries. And there's some mysteries to be solved. For example, I'm not going to go into details, some Jupiters are way larger than theory can predict. So we find some hot Jupiters that are about more than 2 times larger than Jupiter in size. And this is really, really at odds with theory. It's so-called radius inflation, and there's no good reason for this. There's no good theory explaining this. So these are these super large and super low density exoplanets. It's also not clear. Remember that I talked about an area where some planets could be gaseous and some planets could be rocky. This transition between gaseous and rocky planets is not well understood. So it's not clear how a planet gets to grow to make it a gas planet, or sometimes they end up as bare rocks, as our own Earth. So it's not really understood how this transition, how planetary models can form these kinds of exoplanets. And there's ongoing research on trying to understand these features. And so the next step is, okay, we talked about planet detection. We talked about detecting with transits, with radial velocities. So let's go into exoplanetology. So let's try and understand what planets are made of. And planets are made of by understanding, well, the technique that we use is transmission spectroscopy. So let's imagine that we have a planet which has no atmosphere, and we measure this planetary transit depth as a function of wavelength. So if it's really a circle, a dark circle, then the depth will be independent of wavelength, right? So this would be flat. But let's imagine that this planet is surrounded by an atmosphere, which is this ring, as projected here, which is semi-transparent, right? So there's some wavelengths where gases are opaque, and some wavelengths where gases can be transparent. So then if we measure the depth of this transit as a function of wavelength, there's going to be some variability. And this variability is what's called the transmission spectrum. So it's light shining through the atmosphere of this planet that has imprinted let's say, the chemical compounds that are in this atmosphere, right? So we have a number of compounds, water, CO2, methane, and then these compounds have a specific transmission spectrum. You shine starlight through this atmosphere and we register that, and this starlight would have imprinted the absorption or transmission from these chemical compounds. So this technique was pioneered by Sarah Seeger in 1999, and she got half of the Kavli Prize also this year. So we've been doing this already with Hubble Space Telescope, and here are about 10 transmission spectra of 10 hot Jupiters. So these are the little dots there, and the model is shown here with thick lines with different Jupiter-type planets, and all these wiggles that you see here going up and down and so on, these are signatures of chemical compounds on these atmospheres of these planets. So sodium, potassium, water vapor, and so on. You see these features here. And then maybe it's not so clear here, but then we got, about 2 years ago, we got the James Webb Space Telescope, and things cleared up an enormous deal. So these are transits, real transit observations with JWST, and this is one of the spectra of JWST. This is transit depth in percentage as a function of wavelength, and all the measurements here in black, and you see this is a model, and each of the shaded regions represents one chemical compound. So you can see the CO2 here in big amounts. There's water vapor in blue a lot. There's methane, and there's all sorts of chemical compounds that are seen here in transmission. Again, so this is starlight shining through the atmosphere of the planet and imprinting here the transmission spectrum of these chemical compounds on the atmosphere. So this is the way that we have to detect or to determine compositions of atmospheres of exoplanets. Okay, I can jump over this one. This will be done also in very big numbers with another mission that we're also involved in. That's called the Ariel mission. Ariel will be launched in late 2029. And we're talking about here getting not a spectra for not only a handful of exoplanets like JWST is doing, but for about 1,000 transiting exoplanets. So the Ariel will produce a collection of spectra of exoplanets, and then we can understand chemical families, let's say, and do some ensemble analysis to try and understand the population of exoplanets. So maybe a couple of minutes on the challenges. This all seems very simple, very easy, and all already done, but we are facing big challenges to get one step beyond this. And one big challenge here is to go over something called stellar activity. As you know, the sun has sunspots and has a sunspot cycle, and those sunspots are active regions on the surface of the sun. And those active regions change over time, those sunspots change over time, and also they rotate with the sun. So that kind of variability on the star wreaks havoc on our ability to measure these velocities and these brightnesses at very high precision. So since stars vary, all the techniques that I've been discussing rely on the star being extremely stable, right? Because if the star changes, then the whole thing goes to hell. But if stars do change, and as you can see in a little video, so there's a sun with some spots, some active regions, and they rotate, they change over time and so on. And this effectively makes that this is radial velocity detection of exoplanets. This is the semi-amplitude of planet detection as a function of discovery year, and we're sort of stuck. So there's few exoplanets down there, but we were really going like crazy, like 2000, 2005, 2010. But since then, instruments are no longer the problem here. We have really precise instruments getting very good measurements down there, but we cannot beat the stellar noise, let's say. And that's the goal here. The fundamental limit is no longer instrumental, but astrophysical. And this is the kind of thing that I was recently awarded an ERC advanced grant exactly for this. So to try and get all these exoplanet and target monitoring data together with some modeling to try and reduce this, let's say, floor that we have now at 1 meter per second of sorts down to 10 centimeters per second, and do spectroscopy also to better level. So this is the so-called Spotless project. That's the ERC funded. And the idea is to use novel techniques, machine learning, and other Gaussian processes and other techniques to try and reduce this floor to enable the detection and discovery of Earth-like planets or Earth analogues. Because the goal here is to go to the next step. So I think I may have convinced you that we know that there are other planets out there. So there's almost 6,000 known already. We are kind of understanding how they form and evolve, although there's still some unknowns, of course. We're trying to know what they're made of with JWST, with Ariel in the future. But then the question is, are they habitable? So could they harbor life? And are they actually inhabited? So do they actually have a biosphere on the surface? And this is the next revolution, I understand. I mean, I think for humankind. 4 centuries we are 4 centuries after the Copernican revolution, where our place in the universe was sort of defined, and now we have to define our context in the living universe. That's our next step, to try and see whether our planet is unique or whether our planet is one among many living planets out there, right? So the concept here is the so-called habitable zone. So a planet that lies in this habitable zone could have liquid water on the surface. So the habitable zone around the star is defined as a range of orbital distances where a planet that has rocky composition could harbor a surface liquid water. And this is, of course, an equilibrium. So there's incoming radiation from the star, there's outgoing radiation from the black body of the planet. And then you can work the numbers out, and you can calculate this blue area here for the sun and for other kinds of stars as a function of orbital distance. And when you see our solar system here, Venus was in the habitable zone. It's probably no longer. Your Earth is comfortably within the habitable zone. Mars is in the habitable zone of our still solar system, although it had problems because it's too small. And then the main thing here, I'm not going to discuss in detail, is not just about equilibrium temperature, it's also about greenhouse gases, right? So you have an atmosphere that can have CO2 as a regulating agent. So you can get close to the star, and then you remove CO2, and there's less greenhouse. You move away from the star, you can add CO2, and then it warms the surface of the planet. And that's why the habitable zone is so wide, let's say, in this. The equilibrium temperature of the Earth is minus 18 degrees centigrade, and there's 33 degrees caused by greenhouse gases in our planet, which bring the average to about plus 15 C. So greenhouse gases are very good, let's say. It's not that the bad thing is that we're trying to move them and to change the amount of greenhouse gases, but they are absolutely essential to a planet because this is the agent that regulates climate. So how many of these 5,800 planets that we know are potentially habitable? And this is the collection. This is the collection of today's known potentially habitable planets. Sorted by distance, Proxima Centauri and beyond that. And by the way, all these we have found here in the group at the Institute. All these nearby exoplanets, potentially habitable, we found in the group. So in this 29, I call potentially habitable planets that are in the habitable zone are rocky. These are the 29. So how many of these are actually habitable, meaning that they have surface liquid water? We don't know. We don't know how many of these that are in the right position and have the right size actually hold water. How many are these inhabited? Even less. And how many of these are suitable for humans, or we can breathe there? So probably even less, right? So we are just at the first step in this quest to try and get to inhabited planets and try and understand them. And can we do this? Yes. Can we find life remotely on exoplanets? And the answer is yes. And we can do it using remote sensing and using the same techniques that I explained to measure or to understand the atmospheres of these exoplanets. Because there may be chemical compounds on the atmospheres of exoplanets that give away that these planets have a biosphere. Some chemical compounds that cannot be explained only by geology, but you have to resort also to biology to explain them. And this is what we call biosignatures. So these would be objects, substances, or patterns that require a biological agent. And we do this with remote sensing. We cannot take a picture with all the continents and seeing the Amazon and seeing the green forest and so on. We have to contend with using measurements of integrated light from the planet. And so that's what we're doing now to trying to devise these biosignature gases. So if we take, for example, Venus, or you take Earth, there's a mixture of gases. This is the Earth spectrum. So this is features of oxygen, ozone, water vapor, CO2, in some places methane as well. And these combinations of gases that we have now on the Earth that we're breathing right now can only be explained by the presence of a biosphere. Because, for example, we have a combination of oxygen plus methane, which are not long-term stable, let's say, because they react with each other. And therefore, the fact that we are simultaneously having in our atmosphere oxygen and methane, that's a biosignature, bioindicator. Typically, it's out of equilibrium chemistry. So the goal here that we have for, let me just jump over this. The goal for the long run, let's say, for the 2040s, which is bad, it's to build instruments like this so-called Habitable Worlds Observatory, or this mission called LIFE, that should be able to really take pictures of Earth-like planets, get spectra of those Earth-like planets, see what chemical compounds those spectra have, and then maybe claim an indirect detection of life, because some chemical compounds cannot be explained unless we invoke some biology, let's say, not only with geology. And again, it will be an indirect detection of life. It would not be a direct detection, but indirect detection from the chemistry, from the byproducts of biology, let's say. So these are missions that are not, this mission is already approved by NASA and it's already in development. And it says the idea or the plan is to fly it like early 2040s. LIFE is not even approved by ESA, and also it will be to fly between 2045 and 2050. These are the timescales that we have, which is, yeah, I don't like that anyway. It's way too late. So, but they're expensive. So anyway, and there's some technology to be developed. So the overall goal here is to, I've been discussing instruments, right? So this is a very busy plot, but just the idea here, these are space missions that are related to exoplanets. These are telescopes and instruments on the ground that are related to exoplanets. Some are in the past or in the present. Some are currently flying, and some are for the future, or some are for the far future. And with this goal, let's say, of understanding better and better how exoplanets form and evolve, understanding their chemical composition and what they're made of, and potentially also finding Earth-like analogues and being able to characterize their atmospheres and see if they have chemistry that would be indicative of some biosphere on the surface. So the goal for the future is to take pictures like this. Do you know what this iconic picture is? Have you ever seen this? Yeah, some people are nodding, right? This is the pale blue dot. This is a picture of our Earth from 6 billion kilometers. Taken from Voyager 1. This was a picture that was asked by Carl Sagan to be taken. So, and this is our Earth in 1 pixel on the detector. So the idea that we have for the next 20 years or so, next 2 decades, is to be able to develop technology to take pictures of planets in 1 pixel, let's say, and then to understand, to get spectra of that light in 1 pixel, and then to find the indications of life. So that's our quest for the next 20 years or so. And I'll stop here. And okay, thanks.
Thank you, Ignasi. What an amazing talk. Do you have any questions in the audience?
This out of equilibrium chemistry cannot be driven by orbit or
Could be. For example, if the orbit is circular, then you don't expect many changes. If we have some obliquity in the rotation axis of the planet, then you have seasonal changes, which can be understood as well. And if you have elliptical orbits, then there may be some changes there as well. It's more than the orbital changes, it's more of geological sources. For example, there's oxygen on Mars, and this oxygen is from reaction of from water photolysis. So so this can create oxygen, and so there's also methane on Mars. So the thing is that it will be a bit difficult to understand if we see some chemical compounds in some amounts, whether those amounts can be explained by geology or that we need to resort to biology. This will be probably the most difficult thing. There's no indicator of let's say on this bioindication gas that will be just unique. So if we see that, then it means that there's some biology. There's so-called technosignatures. So if the planet is full of CFCs, as we had our Earth 20 years ago, this is usually because some technology is doing things really wrong, as we did, right? And we are still. But in terms of general gases in biology, it's going to be tricky. But then the thing is to find different planets with different occurrences, different instances, and to try and find a common pattern, let's say, and that could be biology in all cases. Yeah. Yeah, that's a very good question. When the rotation of the star is similar to the rotation period of the planet, we're dead. There are some cases where we can distinguish things, but when rotation happens over different timescales, then it's not so difficult. But in any case, there is more than rotation. There's also surface variability. So those spots grow and decay, and that gives rise to a number of different timescales. And so let's say the power spectrum or the spectrum of this variability has frequencies activated on many, many different places, and it's really difficult to tell them apart. There are some tricks that we play, is that, for example, activity effects are chromatic. So they're depending on wavelength. So activity has a stronger effect on bluer wavelengths than on red wavelengths, both in transit and also radial velocities, while Keplerian motions are physical effects. They're independent of wavelengths. So we can play some tricks to try and decorrelate some of these stellar noise, but it's definitely the problem that we have right now. Yeah. So let's say my goal in the project is to turn this, let's say, this noise into signal that we can model. So if we can model or simulate that noise, then it becomes that we can understand. It means that we can understand it and maybe correct it out. That would be the idea. Yeah.
So I also had a question about the calibration that you said
Yeah.
that was introduced about 30 years ago with the laser. I guess this is what when you see the pictures of this telescope.
No, that different thing. Yeah, the thing that you see with a laser shooting out of a telescope dome, that is a laser that ionizes the sodium layer on the atmosphere of the Earth and creates an artificial star. And then the telescope uses that artificial star to correct the image, because we know that it's a perfect image, let's say. And then because of turbulence, the front wave will get distorted, and is used to this so-called adaptive optics. So we get this artificial star next to our star. In the case of spectroscopy to find planets, we're shining a light. We have a calibration lamp, let's say, and that lamp can be a laser. That's called a laser frequency comb, or a hollow cathode lamp, and that goes up to the telescope and back in and down, following the same pattern, the same path as the starlight, and goes into the instrument.
Where the light is collected, where is that coming from? Does it shoot out to the microphone?
No, you have a fiber. They have a calibration lamp somewhere. You have a fiber that goes up to the focus of the telescope through a fiber, and then there's an injection system where that light goes into another fiber that mimics the same path that the light from the star follows. And there it's affected by the same environment effects as a starlight, but never goes out, let's say. It goes through a fiber up to the top and then re-injected into another fiber like it was a star as well. Yeah, yeah. I think, yeah.
Thanks for the presentation. At some point, you mentioned that it seems that some planets start far away from the corresponding star, and you said, I mean, that my understanding was that they move approaching the corresponding star.
Yeah.
But I saw that the period of rotation gets much shorter.
Yes.
So it approaches this rotating faster and faster.
No, they lose angular momentum, so the orbital frequency gets much higher, and the period gets shorter because they have a stable orbit. So it's like a spiraling in effect. The rotation of the planet itself can be altered, but not necessarily. But yeah, it's a process where the planet loses angular momentum. Ah, very good. Because
that going inside should rotate faster, but it goes the other way around.
well, because it goes into a stable orbit at every time. So a stable orbit, the rotation, the speed of the orbit is a lot larger when you are in the farther distances, right? Because you have to go, and as you go in, the speed of the orbit gets slower, and that means that it has lost also angular momentum. And the way it loses angular momentum is that because when planetary systems form, they form from something called a protoplanetary disk. So you have the star and a disk of material. And that disk of material, there are some places where the material gets clumped together, and that accretes more material, and then it becomes a planet. Right? But when that planet forms, which usually timescale is of order of maybe 10 million years, and the disk lasts for maybe 30 or 50 million years, you have a planet and you have a disk of material. And by interaction of this planet with the disk of material, there's this migration that it breaks the planet, let's say. Breaks, I mean, it stops the planet. And it spirals in. And then when the disk is cleared because the star becomes bright enough, then it stops. And sometimes it doesn't stop. I'm sure there are many planets, we're sure that many planets get engulfed by the star. So they actually fall into the star because they cannot stop this migration process. And some other planets get expelled in the interstellar medium as well, because they have interactions there. So one thing that we learned is that planetary formation is a lot messier and a lot more dynamic than we expected. So there's many things happening. Planets moving back and forth, planets being expelled of planetary systems. So we think there's more planets, there's at least the same amount of planets free floating in the galaxy than there are in orbits around stars. So this formation process is very chaotic and very violent, let's say. Yeah, it's not good. And then you may think, well, why did this not happen to us? Well, it probably because Jupiter took a bit longer to form than it was expected in a way. The disk cleared also a bit fast. And then the architecture of the solar system with Jupiter and Saturn sort of pulled Jupiter's not to fall too far in. But actually, Jupiter did start migrate inwards. And then what happened is that it exerted a strong influence on Mars, and Mars could not grow as much as it should have. And also there's the asteroid belt, which is also material left over. Then eventually Saturn, because of orbital resonances, pulled Jupiter back into farther orbits, and then it went to the current location. So that explains something that you may think: Mercury, very small; Venus, larger; Earth, a bit larger; Mars, small again; and Jupiter, very large. So what happened to Mars, right? Because if it's a sequence, why didn't Mars didn't grow beyond that? Because it's 1/10 of an Earth mass. So the reason is because Jupiter didn't allow it to grow, let's say. And it was this motion of planets back and forth, let's say, that had that effect. Yeah.
Please.
You use sometimes the spectroscopic pictures of satellites orbiting the moons, orbiting around the planet, to get a reference calibration for, I wouldn't say not like in astrobiology, but just for position. Is that something that is normally done?
It's done. It's when we do this so-called comparative planetology, which means that we try and see what patterns we see. We use the spectra for Jupiter, for the moons of Jupiter, for the moons for Saturn, the moons of Saturn, and whatever is there, including the Earth, by the way. And it's very interesting to, I mean, how can we know the spectrum of the Earth, right? If we never see Earth as one dot, right? And there was a very clever technique that was used by a colleague of mine who's now in Enrique Pallet in the Canary Islands. that used a lunar eclipse to get the spectrum, the reflected spectrum of the Earth. Because during a lunar eclipse, the dark side of the moon, the dark part of the moon, is actually slightly lit by the reflection from the light on the atmosphere of the Earth and back into the moon. So he took a spectrum there, and he was able to get these indications of water vapor, CO2, all these different molecules that are in our atmosphere through this reflected light during eclipse. And yes, we use that as well. And this is the input to try and see how we can characterize the atmospheres of exoplanets and learn a bit more the chemistry of those atmospheres, which is quite unknown because these are planets that have nothing to do with our solar system planets. If you take Jupiter, which has a temperature of maybe 100 Kelvin, and you put it at 2000 Kelvin, I mean, it's really a completely different regime. So we're trying to learn how this would work. But yeah, and we use everything at hand. Yeah. Yeah.
The existence of macromolecules, could that be like larger molecules? Could that be indicative of
yeah. The thing is that right now, we are typically only sensitive to the biggest, the large constituents in terms of mass fraction, let's say, and bigger molecules tend to be trace constituents. And we do find big molecules in the interstellar medium, and therefore we expect them to be also in the atmospheres of exoplanets. But it's really hard to measure that, and it's even hard because sometimes we can only measure molecules that have a spectral signature. For example, in our own atmosphere, 78% is molecular nitrogen, which is invisible to all of this. So our substrate gas cannot be found because nitrogen has no features in this spectra that we have. So if we took our own planet, we wouldn't see much, actually. We would see that oxygen is there, but not because of oxygen. The main constituent that we can actually measure is ozone, which has a strong infrared feature as well. CO2 is also very prominent. Water vapor is also very prominent. So we have to find sort of proxies from some molecules, and large molecules are difficult to find. There was very interesting, there was a couple of years, 3 years ago, 4 years ago, do you remember about phosphine in Venus? There was a big splash about phosphine being found in Venus, and it was sort of, there were some indications of this, some suggestions that this could be indication of life on Venus at high surfaces. That's phosphine, so pH 3. And even that is really hard to detect on exoplanets. And we don't expect to have that, although it would be a very, very good biology indicator. Yes.
No more questions. Okay, let's thank Ignasi again.
My pleasure.